Hey everyone, it's Mark Pinion. Today we will be looking at oscillatory motion and how the energy principle applies to this motion. In our analysis, we look at oscillation in two directions, both x and y. As the spring mass system moves, we observe changes in kinetic energy and potential energy. The change in total energy is the sum of these two quantities, and in our case is assumed to be zero, meaning no work is done on the system and no energy leaves or enters the system. Since we know that delta E is zero, we can rearrange the energy equation to see that the changes in potential energy are equivalent to the changes in kinetic energy. They are inversely related. A change in one elicits an equal and opposite change in the other, conserving energy and demonstrating the energy principle. Using tracker, we gather motion data of the weight as it moves with the spring. Upon analyzing the y and x data, position data, we can determine the period of oscillation for the system, the time it takes for one cycle to occur. After manipulating some equations, we can solve for the spring constant using the period we just found. I used the period given in the lecture video, which is 1.52 seconds. This yielded a spring constant of 6.87, just like in the lecture video. Now, using our knowledge of static equilibrium, we can then solve for the relaxed length of the spring. Since at static equilibrium, spring force equals weight force, we can equate the two. After a bit more algebra, we can get an easily workable form to solve for L naught, which came out to be 0.123 meters after plugging in the appropriate values, just as in the lecture video. As you can see here, the red ball representing the observational data gathered through tracker and put in Excel for the VIDLE to read matches up fairly well with the blue ball representing the computational model's prediction. They are very close the entire time, meaning our computational model does a very good job of predicting the motion that we observed through tracker. You can see this correlation in the graphs as well. As you can see from the graphs, the model does an excellent job of predicting the motion. It's almost an exact fit in both x and y directions. One more important thing to note here is the blue and black arrows. The black arrow represents the gravitational force on the mass, and the blue arrow represents the spring force. The spring force changes depending on the stretch of the spring, as it should, while the black gravitational force remains constant, as it should. In this graph pictured, we have the change in potential energy of the spring in red, the change in the potential energy, the change in gravitational potential energy in green, the change in kinetic energy in blue, and the change in total energy in yellow. It's important to note here that delta E in yellow remains static at zero for the entire duration. This lack of change in total energy makes sense, as work is not being done on the system. The changes in the other energy quantities all balance each other out, so that as one increases, the other two adjust accordingly, so that the system's total energy does not change. For our what does it mean question, we look into the period of oscillation. The period of oscillation of a spring and mass system is dependent upon the mass and the spring constant. But in our case, our system works as a spring and pendulum hybrid. This causes the period of oscillation found from analyzing our x motion to be slightly inaccurate, especially when combined with the angle at which we initially release the mass. The effect that this has on the y motion isn't as pronounced, and as such, I used the y period in my calculations. This value is also the same one from the lecture videos, 1.52 seconds. After all this analysis, we can say that the energy principle in action. Conservation of energy occurs as kinetic energy is converted into potential energy in the spring and gravitational potential energy, which in turn is converted back into kinetic energy as the mass oscillates. Since zero work is done on our system, our change in energy is zero, and the change in potential energy and the change in kinetic energy always add up to zero. Thank you.